Subscribe to the channel so you don't miss out on any of these videos. Imagine staring up at the night sky, surrounded by a vast, silent emptiness. It's a darkness dotted with light, each point a star, perhaps even a galaxy, a cosmic entity millions or even billions of years old. As you gaze, the sheer scale and mystery of it all tugs at your thoughts, asking a profound question: what is the ultimate shape of the universe? Will it keep expanding forever, or does it have an end waiting somewhere in the unimaginable future? The idea that our universe has a shape, a structure, and a destiny has captivated cosmologists, philosophers, and dreamers alike. This mystery goes beyond what the eye can see, leading us into a realm of mind-bending theories and hypotheses about the very nature of existence. Today, let's embark on a journey to explore what science suggests about the shape and fate of the cosmos. The study of the universe's shape and destiny is at the heart of cosmology, the branch of science that seeks to understand the structure, origins, and fundamental mechanics of the cosmos. For most of human history, questions about the universe's shape and fate were relegated to the realm of philosophy and theology. With the rise of modern science and advancements in astronomical technology, however, we've been able to peer deep into the cosmos and begin answering questions that seemed unapproachable. Yet, even with all our modern tools, the mysteries surrounding the shape and fate of the universe remain elusive, with theories as diverse and intriguing as the universe itself. At the heart of the quest to understand the shape of the universe are three primary models: a flat universe, an open universe, and a closed universe. Each of these models represents a distinct idea about how space is structured on a cosmic scale and what that means for the future of everything we know. The flat universe model suggests that, like a two-dimensional sheet, the fabric of space is perfectly balanced, stretching out infinitely with no curvature. This model implies a sort of cosmic equilibrium, where the forces at play balance each other perfectly. It's a model that aligns closely with what we observe through cosmic microwave background (CMB) measurements, which indicate a universe that is very close to flat. The implications of a flat universe are profound, suggesting a cosmos that will continue expanding at a steady pace, neither collapsing back on itself nor accelerating into an ever-widening void. On the other hand, the open universe model proposes that space has a hyperbolic, or saddle-like, curvature. In this scenario, the universe would expand forever, but in a way that causes galaxies and matter to spread out at an increasing rate, leading to a scenario of eternal isolation. With an open universe, everything we know would eventually drift apart, growing so distant that the night sky would one day appear empty, devoid of stars. This model paints a haunting picture of a universe where matter is stretched thinner and thinner, a fate that's both fascinating and eerie. Then there's the closed universe model, which posits that space is curved inward like the surface of a sphere. In this case, the universe's expansion could eventually slow down, stop, and then reverse. Such a model leads to a theoretical fate known as the Big Crunch, where, after reaching its maximum expansion, the universe would begin contracting, eventually collapsing back into an unimaginably dense point. The closed universe model presents a cyclical vision of cosmic evolution, where expansion and contraction are part of an endless loop of cosmic rebirths. As we delve deeper into the fate of the universe, we encounter three major theories that address what might ultimately happen to space, time, and matter: the Big Crunch, the Big Rip, and heat death. Each of these theories presents a unique and challenging picture of the universe's end, raising as many questions as it answers. First, the Big Crunch, tied closely to the closed universe model, suggests that if gravity overcomes the momentum of expansion, the universe could reverse its course. Under this scenario, galaxies would begin to move toward each other, and the cosmos would compress back into a hot, dense state similar to the one from which it emerged. This collapse would continue until everything merges into a single, infinitely dense point, potentially leading to a new Big Bang and a rebirth of the universe. The Big Crunch is a captivating concept because it envisions the universe as cyclical, with a future that ultimately mirrors its past. Yet, for this fate to be realized, certain conditions regarding matter density and cosmic forces would need to be met, conditions that current observations suggest might not align with our universe's characteristics. The Big Rip offers an entirely different outcome, one that arises from the notion of dark energy. This mysterious force, observed as a form of energy that seems to accelerate the universe's expansion, is still not fully understood. If dark energy continues to drive expansion at an ever-increasing rate, it could eventually tear apart galaxies, stars, planets, and even the atomic structure of matter itself. The Big Rip would be the ultimate act of cosmic disintegration, an event in which all that exists is gradually torn apart until there is nothing left but an infinitely vast, empty void. This fate is terrifying in its finality, a scenario where not only would all physical structures be obliterated, but space itself would cease to have any coherent structure. The third major theory, heat death, also known as the Big Freeze, represents a more gradual, though equally bleak, vision of the universe's end. In this scenario, the universe continues expanding, but instead of an explosive end, everything simply runs out of usable energy. Stars would exhaust their fuel, ceasing to shine, and galaxies would grow dimmer as stars die one by one. Eventually, black holes, the last remaining active structures in the cosmos, would also evaporate through Hawking radiation, leaving behind a cold, dark, and inert universe. Heat death paints a picture of eternal stillness, a universe devoid of heat, light, and activity, where entropy has reached its maximum and no further change is possible. Each of these theories relies on different assumptions about cosmic forces and the nature of dark energy, an enigma that continues to puzzle scientists. Dark energy was first discovered in the 1990s when astronomers observed that distant galaxies were accelerating away from us, suggesting an unseen force driving this acceleration. Though we still don't fully understand dark energy, it constitutes about 70% of the universe's total energy content, making it a dominant factor in cosmic evolution. Depending on how dark energy behaves over time, it could lead us down any of these pathways to the universe's end. But even as we consider these theories, there's a fundamental question at play: why does the universe expand at all? To answer this, we turn to the concept of inflation. In the early universe, a brief period of rapid inflation expanded space faster than the speed of light, setting the stage for the formation of galaxies, stars, and planets. Inflation theory explains much about the large-scale structure of the universe and why it appears to be relatively uniform. Yet, it also raises questions about what came before inflation and what might lie beyond the observable universe. Could there be regions where inflation never stopped, spawning bubble universes within a greater multiverse? Such ideas stretch the boundaries of what we can comprehend, suggesting that our universe may be just one of many in a far more complex cosmic tapestry. Beyond these mind-bending ideas lies an even deeper mystery about the shape of space itself. While the flat, open, and closed models give us a framework, there are alternative hypotheses about the shape and nature of the cosmos. Some theories suggest the universe might be shaped like a torus, a three-dimensional donut, or even more exotic forms that challenge our understanding of space and geometry. If the universe has a non-trivial topology, it could mean that traveling in a straight line long enough might eventually bring you back to your starting point, much like navigating the surface of a sphere. This kind of geometry, known as finite but unbounded, would mean that the universe is self-contained in a way we can barely imagine. The question of the universe's ultimate fate forces us to confront not only scientific but also philosophical questions about the nature of existence. The Big Crunch, Big Rip, and heat death each imply a different destiny, not only for matter and energy but for the very fabric of reality itself. These theories challenge us to think about time on scales that dwarf human life, encompassing epochs so vast that the entire history of humanity seems like an instant. What does it mean if all that exists will one day be undone? Is there any significance to our lives if everything is destined for annihilation or eternal stillness? The pursuit of answers to these questions is ongoing, with scientists probing ever deeper into the cosmos through observations, mathematical models, and thought experiments. The more we learn, the more complex and mysterious the universe appears, as each answer leads to new questions, pushing the limits of human understanding. Whether we are moving toward a universe that will someday collapse, tear apart, or simply fade into cold darkness, the journey of discovery is far from over. This quest, driven by curiosity and a desire to understand our place in the cosmos, is as boundless as the universe itself. Even as we continue this exploration, it's astonishing to think that our understanding of the universe's fate hinges on tiny particles and forces operating on the smallest scales. In particular, the interplay between matter, and dark energy determines whether the cosmos will end in fiery collapse, total fragmentation, or frozen stillness. Dark matter is one of the universe's most puzzling ingredients. Though it doesn't emit light or energy and can't be directly observed, dark matter interacts with visible matter through gravity, acting as an unseen framework that holds galaxies and clusters of galaxies together. In fact, without dark matter, the universe as we know it would look drastically different, and galaxies wouldn't be able to form or maintain their structures. Scientists estimate that dark matter makes up about 27% of the universe, leaving only 5% as the familiar matter we can see and interact with. This distribution has profound implications for the universe's destiny. If dark matter and regular matter combined were dense enough, they could exert sufficient gravitational pull to slow down and eventually reverse cosmic expansion, leading to a big crunch. But current observations indicate that there may not be enough matter to overcome the expansion caused by dark energy. Instead, dark energy appears to dominate, pushing galaxies apart and leading to outcomes like the Big Rip or heat death. To complicate things further, we don't yet fully understand the properties of dark energy, or if it might change over time. If dark energy were to gradually weaken, for instance, gravity could still have a chance to slow down expansion, allowing for a big crunch. On the other hand, if dark energy were to strengthen, it could lead to the Big Rip sooner than expected. This potential for change keeps scientists intrigued, and slightly unsettled, about what might lie in store. One of the most significant discoveries that deepened our understanding of cosmic expansion came from the observation of Type Ia supernovae. In the late 20th century, astronomers studying these standard candles observed that distant galaxies were not only receding from us but were doing so at an accelerating rate. This finding was shocking because it implied that some unknown force was acting against gravity, causing the universe to expand faster over time. This observation led to the Nobel Prize-winning conclusion that dark energy exists, although what dark energy actually is remains one of the greatest mysteries in cosmology. The study of the cosmic microwave background (CMB) has also been pivotal in our exploration of the universe's shape and fate. The CMB is the faint afterglow of the Big Bang, a relic of the universe's infancy, frozen in time and stretched across the cosmos as a faint radiation field. By analyzing slight fluctuations in the temperature and density of the CMB, scientists have been able to glean insights into the universe's geometry and its composition of matter, and dark energy. These measurements suggest that the universe is flat, or very close to flat, which aligns with the concept of a steadily expanding cosmos rather than one destined to collapse. But while a flat universe might point toward an endless expansion, the influence of dark energy adds complexity, making it difficult to predict how long expansion might last and at what rate. Another fascinating aspect of the universe's potential shape is the idea of cosmic inflation. In the moments following the Big Bang, the universe underwent a period of rapid inflation, expanding faster than the speed of light. This inflationary epoch smoothed out the universe, explaining why it appears so uniform on a large scale. However, the mechanisms behind inflation remain speculative, with some theorists suggesting it could still be happening in isolated regions of space, creating a multiverse, where bubble universes pop into existence independently of our own. If this multiverse theory is true, it challenges our understanding of the universe's shape by implying that our observable cosmos is only a small part of a far larger, possibly infinite, structure. While these theories about the universe's shape and fate are rooted in scientific observations, they also touch on deeply philosophical questions. If the universe is flat and destined to expand forever, then every galaxy, star, and atom we know will eventually drift into isolation, leaving the universe as a dark, empty expanse. In this scenario, all forms of life would eventually face extinction, with no way to rebuild or renew. Heat death, then, is not just a scientific concept but a contemplation of ultimate isolation and entropy, where even memory, information, and structure are eventually erased. The thought of a universe that ends in isolation, silence, and cold can be unsettling, yet it's a fate that aligns with the principle of entropy, where systems naturally move toward disorder. On the other hand, the Big Rip scenario, while equally bleak, implies a universe with a dramatic, albeit cataclysmic, end. This theory suggests that dark energy, if it continues to grow in strength, could eventually overpower every force in the universe, tearing galaxies, stars, planets, and even atoms apart. The Big Rip would be the ultimate act of cosmic destruction, leaving nothing intact, not even the fabric of space-time itself. This fate might seem horrifying, yet it's also a profoundly energetic vision of the universe's end, one that embodies cosmic power and an unstoppable force. Unlike heat, death, slow decay, the Big Rip suggests a finale that is sudden and absolute, with all matter torn apart at an accelerating rate. The Big Crunch, though currently the least supported by observations, presents a unique philosophical proposition. If the universe is indeed closed and gravity ultimately overcomes dark energy, the universe would reverse its expansion, collapsing back to a dense, hot singularity. This cycle might suggest a cosmos where birth and death are not endpoints but rather phases in an eternal cycle of big bangs and big crunches. A closed universe and a big crunch would imply that life, stars, and galaxies might rise and fall in an endless sequence, each universe starting anew from the ashes of the old. The concept of multiple universe cycles leads us to yet another fascinating theory known as the cosmic bounce. This model suggests that a big crunch could lead to a big bang, with the universe continually rebounding and regenerating itself. In this scenario, our universe could be just one in a sequence of countless past and future universes. Each cycle could bring about a slightly different set of physical laws or configurations, meaning that each iteration of the universe would be unique. This idea, while highly speculative, offers a hopeful perspective on cosmic mortality. Instead of seeing the end as final, it suggests that the universe has a kind of resilience, an eternal return that ensures existence always finds a way to begin anew. There are other, even more speculative theories about the universe's fate that venture into realms bordering science fiction. One such idea is the concept of quantum immortality, which emerges from the many worlds interpretation of quantum mechanics. According to this view, every quantum event creates a new branch in the universe, leading to a multiverse where all possible outcomes are realized. In this context, some have proposed that, theoretically, there might always exist a universe where life continues, even as other branches face heat, death, a big rip, or a big crunch. Though this theory is far from proven and remains largely theoretical, it offers a fascinating glimpse into the potential for infinite survival through the multiverse. The sheer diversity of theories on the universe's fate highlights just how much remains unknown. Each model depends on variables that are not fully understood, particularly the behavior of dark energy over time. If dark energy is constant, a flat or open universe might lead to a big freeze. If it strengthens, we may see a big rip. And if it decays or changes, a big crunch could still be possible. As scientists continue to study dark energy and refine their measurements of the cosmic microwave background, we may one day gain more definitive answers about what the future holds. But for now, the mystery remains as vast as the universe itself, a cosmic puzzle with pieces that may never fully fit together. In pondering these grand cosmic questions, we're ultimately forced to confront our place within the universe's vast scale. Whether the universe ends in a fiery collapse, a silent freeze, or a cosmic tear, our existence is but a fleeting moment within its history. Yet, it's precisely this ephemerality that gives life its poignancy and beauty. We may not have control over the universe's destiny, but by seeking to understand it, we affirm our curiosity, our resilience, and our capacity to wonder at the infinite. The mystery surrounding the universe's fate draws us deeper into questions about existence, consciousness, and the very nature of time. While scientific theories like the Big Crunch, Big Rip, and heat death give us frameworks to explore possible cosmic endings, they also touch on philosophical realms that go beyond mere physics. These theories do more than predict events millions or billions of years in the future. They challenge us to think about what an ending means on a cosmic scale. If time itself ceases to exist, then what remains? Is there a concept of before and after, when the fabric of space and time collapses or freezes? These are questions that are both exhilarating and haunting. One of the intriguing perspectives on the universe's end is that time, as we understand it, may be an illusion or an emergent property. Some physicists and philosophers argue that what we perceive as the flow of time might not be fundamental to the universe. Instead, time could be a construct of human consciousness, a way to organize events within our minds. This concept aligns with certain interpretations of quantum mechanics, where the notion of time as a linear, unidirectional progression is less certain. If this is true, then contemplating the universe's end from our time-bound perspective may be akin to asking a fish to understand the concept of dryness. It's simply outside our frame of reference. Another aspect to consider is the anthropic principle, which suggests that our universe is observable in the way it is precisely because it supports life capable of observation. Some theorists argue that the conditions and constants of our universe are fine-tuned for life, making it not only possible but also inevitable that observers like us would arise to ponder these questions. In this view, the universe may have an endpoint in one of these proposed scenarios, but this end is intertwined with our own existence. If no conscious observer remains to witness the universe's demise, does it truly end in any meaningful sense? This idea adds a layer of philosophical complexity to our scientific models, prompting us to ask not only how the universe will end but also who will be there to observe it, if anyone at all. In the search for answers, some scientists and thinkers turn to the notion of a final theory, an ultimate understanding of the universe that would explain its origin, shape, and fate in a single, comprehensive framework. The pursuit of this theory has driven scientific inquiry for centuries, from Einstein's theory of general relativity, which describes the large-scale structure of space-time, to quantum mechanics, which governs the behavior of particles on the smallest scales. However, these two pillars of physics are famously incompatible, and finding a way to reconcile them in a theory of quantum gravity remains one of the biggest challenges in science. A successful theory of quantum gravity could reveal new insights into the universe's shape and the role of forces like dark energy, offering clues to whether it will end in a big crunch, a big rip, or heat death, or perhaps something entirely unexpected. One of the most promising candidates for a final theory is string theory, which proposes that the fundamental constituents of the universe are not particles but tiny, vibrating strings. These strings could account for all known forces and particles, uniting gravity with quantum mechanics in a single framework. In string theory, the universe's shape becomes a matter of how these strings vibrate and interact within higher dimensional space. Some versions of string theory suggest that our universe might be a brane, floating within a larger, multidimensional bulk, with other branes or universes existing alongside ours. In this scenario, the fate of our universe might not be an isolated event. Instead, our universe could potentially interact with or even collide with another brane, sparking new cosmic events that we can only begin to imagine. Furthermore, in some interpretations of string theory, the universe's expansion could eventually slow down, reversing into a collapse that leads to a big crunch, or it could expand indefinitely, with the big rip tearing it apart. In such models, the end of one universe might pave the way for the birth of another, as the energy from one cosmic cycle is transferred into the next. This concept of a cyclical universe suggests that universes may come and go in an endless chain of creation and destruction, each one with potentially different physical laws and constants. Some theorists propose that each cycle might involve slight variations in these constants, leading to an evolutionary process in which universes develop conditions increasingly suitable for complexity and perhaps even life. Another theoretical framework that addresses the universe's shape and fate is loop quantum gravity, which seeks to unify general relativity and quantum mechanics by treating spacetime itself as composed of discrete, quantized loops. Unlike string theory, which relies on extra dimensions, loop quantum gravity suggests that spacetime is granular at the smallest scales. This quantization could provide a natural way to prevent the singularities that occur in general relativity, such as the infinitely dense state at the Big Bang or in black holes. In this view, a collapsing universe might not reach a singularity but instead bounce back, leading to a new expansion phase. This concept of a big bounce aligns with the idea of a cyclical universe, where each bounce initiates a new cosmic epoch, possibly with different physical properties. These speculative theories continue to evolve as we make new observations and develop better models of the universe. Tools like the James Webb Space Telescope and future gravitational wave observatories could reveal phenomena that were previously hidden, offering more clues about dark energy, the rate of cosmic expansion, and the universe's ultimate fate. Every discovery brings us closer to understanding the shape and destiny of the cosmos, yet it often raises more questions than answers, reminding us of the vastness of the unknown. The possibility of an oscillating universe, where big bangs and big crunches follow one another in a perpetual cycle, raises an intriguing question. Could there be remnants of past universes lingering in our current one? Some physicists speculate that traces of previous cycles could be imprinted in the cosmic microwave background, the faint radiation left over from the Big Bang. If these traces exist, they might offer hints of past universes, potentially revealing information about the physical laws and structures that existed before our own cosmic epoch. Detecting such imprints would revolutionize our understanding of time and existence, suggesting that the cosmos itself has a memory that spans beyond any individual universe. Another speculative theory about the universe's fate involves the holographic principle, which posits that the universe could be a projection from a two-dimensional boundary, much like a hologram. According to this idea, all information within our three-dimensional universe could be encoded on a distant, two-dimensional surface at the universe's edge. If true, this would imply that our understanding of shape and fate might be more complex than we realize. A holographic universe might not have a straightforward end in the way we imagine, as its information could persist on this boundary even as the universe's observable contents dissolve or fragment. This theory blurs the line between physics and information, suggesting that reality itself might be a vast data structure that can neither be created nor destroyed, only transformed. The question of information preservation is particularly relevant in the context of black holes, which are often considered portals to understanding the end states of the universe. Black holes challenge our notions of information and permanence because they appear to swallow anything that crosses their event horizon. Yet, according to the holographic principle and recent research on quantum information that enters a black hole might not be lost but could remain encoded on its surface. This idea, known as black hole complementarity, suggests that the universe's fate might also involve a kind of cosmic information preservation. If the entire universe eventually collapses into a massive black hole, could it somehow retain the information of everything that has ever existed? And if so, could this information be reborn in a new universe, echoing the cycles proposed by Big Bounce theories? In many ways, the mystery of the universe's fate is not just about predicting the physical events that may occur billions of years from now, but also about understanding the nature of existence and persistence. The possibility that the universe's memory could survive its own end leads us to speculate on whether life, consciousness, and even individual identities could find a way to persist beyond a cosmic collapse. Though speculative, some theories in quantum mechanics and information theory suggest that consciousness itself might be tied to fundamental properties of the universe. If this is the case, then the end of the universe could have profound implications not only for matter and energy but for consciousness itself. As we contemplate these profound ideas, we're reminded that the cosmos operates on scales of time and space that are almost incomprehensible. Our lives, though brief in the grand scheme, are still part of this vast and mysterious universe. Even if the universe ends in heat death, a big crunch, or a big rip, our existence within it provides a glimpse of consciousness, wonder, and the drive to understand. The knowledge we seek today about the universe's shape and fate is both a scientific endeavor and a reflection of our deepest curiosity, a testament to humanity's desire to connect with the cosmos, even if it may ultimately lead us to a place of silence and mystery. The notion of consciousness in a universe that might one day cease to exist opens another philosophical doorway. Are we, as observers, fundamentally linked to the fate of the universe? The anthropic principle suggests that the universe appears precisely as it does because it allows for observers like us to exist. This concept takes on new meaning when we consider the ultimate fate of the universe. If consciousness, in some form, is intertwined with the universe's structure, then our presence might not be incidental but essential, woven into the cosmic fabric as intricately as matter and energy. This leads to a speculative, almost mystical line of thought. What if consciousness itself is a fundamental component of the universe, just as real and permanent as physical laws? Some theories, like panpsychism, propose that consciousness might be a universal attribute present even at the atomic level, albeit in a form unrecognizable to us. In such a scenario, consciousness could be a property that exists beyond individual beings, perhaps even persisting through cosmic cycles. In a universe governed by cyclical rebirths or a multiverse framework, consciousness might find a way to re-emerge in new forms, becoming an eternal witness to the cosmic dance of creation and destruction. Yet if we lean towards a less hopeful outcome, such as heat death, where entropy reaches a maximum and everything cools to a halt, the future appears bleak from the perspective of life and consciousness. In this scenario, time would stretch endlessly forward in a static, unchanging universe devoid of events, thoughts, or observers. This ultimate equilibrium state would make all distinctions meaningless, rendering the universe a dark, cold expanse where nothing happens and nothing can be perceived. This vision of a frozen cosmos, though stark, challenges us to understand entropy and time itself. It also makes us wonder about the human experience in a universe where, ultimately, decay and dissolution seem inevitable. The idea of entropy is pivotal in understanding heat death, as it dictates that systems move from ordered states to disordered ones over time. Entropy serves as a kind of cosmic arrow, pointing inexorably toward a state of maximum disorder where all processes grind to a standstill. Theoretically, this implies that the universe is constantly losing its ability to sustain complex structures, including those necessary for life. This relentless progression towards disorder isn't merely a prediction. It's an observable trend that plays out even in everyday life, from the decay of matter to the dissipation of energy in stars. Stars burn out, planets cool, and even black holes gradually evaporate, emitting Hawking radiation until they, too, vanish into nothingness. This vision aligns with a universe devoid of renewal, a stark contrast to theories like the Big Bounce or multiverse models. In the heat-death scenario, the final stage is one of eternal stasis, where time becomes irrelevant, as nothing changes to mark its passage. This also has profound implications for how we understand reality, suggesting that everything, even consciousness, is transient, bound by the same thermodynamic limits that govern all matter and energy. This perspective casts existence in a tragic light, presenting a universe that inevitably consumes itself, leaving behind an endless void without memory or meaning. The concept of the Big Rip, on the other hand, brings about a more dramatic vision of the end, where not only does the universe lose coherence, but every constituent part is actively torn apart by an accelerating expansion. If dark energy's influence grows stronger over time, the Big Rip could become unavoidable. Initially, galaxies and galactic clusters would drift further apart, as we see happening today, but the acceleration would continue unabated. Eventually, the force would become powerful enough to pull apart gravitationally bound structures, like galaxies themselves, reducing them to isolated stars drifting through a vast, dark void. Yet the destruction doesn't stop there. As the expansion continues, stars would be torn from their planets, planets from their moons, and eventually atoms themselves would be sundered. At the ultimate moment, even the fundamental particles, protons, neutrons, and electrons, could be ripped from each other, leaving a universe in which even the tiniest forms of matter no longer hold together. In this extreme scenario, the universe would end not as a frozen expanse but as a chaotic storm of particles scattered into oblivion. The very fabric of space-time would become so stretched that it, too, might tear apart, leaving nothing but a literal void where space itself ceases to exist. While the Big Rip presents a scenario where the universe meets a violent and catastrophic end, it also poses intriguing questions about the nature of space, energy, and cohesion. How does dark energy work? and why does it push against gravity? Could there be a deeper, still unknown force that eventually counteracts or stabilizes dark energy? These questions remain unanswered, but every piece of evidence we gather, whether it's the rate of cosmic expansion or the nature of quantum particles, brings us closer to comprehending these grand mysteries. The Big Crunch offers yet another narrative, a universe that, after reaching a maximum point of expansion, reverses its course and begins to contract. This cyclical theory of the universe's fate presents a universe that breathes, expanding and contracting in an infinite cycle of creation and destruction. The Big Crunch is the opposite of the Big Rip. Instead of stretching apart to the breaking point, gravity reasserts itself as the dominant force, and every galaxy, star, and particle is pulled inward toward a single, dense point. This endpoint resembles the initial conditions of the Big Bang, implying that the universe could effectively reset itself, possibly leading to a new Big Bang and the birth of a new universe. This theory raises the possibility that our universe is part of an endless cycle, where each Big Crunch leads to a Big Bang in an eternal dance. In such a scenario, the universe could be a kind of cosmic phoenix, rising from its ashes in a slightly different form each time. However, it also presents a unique challenge in terms of time and identity. If each new universe emerges from the remains of the last, does that mean history repeats itself endlessly, or do slight variations create unique outcomes in every cycle? The possibility of an infinite series of universes has implications for the concept of time itself, as each cycle would reset the cosmic clock, potentially leading to universes that resemble ours, albeit with subtle or even profound differences. Among these theories, one more exotic idea has emerged from quantum mechanics and multiverse theories, that our universe might not be alone. In the multiverse theory, countless universes exist alongside our own, each with its own physical laws, constants, and possible outcomes. Some theorists propose that universes may constantly be budding off from each other, with new universes arising out of the energy fluctuations of existing ones. This multiverse view changes the nature of cosmic endings because, in a multiverse, the end of one universe might not mean the end of all reality. Instead, it might merely be a transformation, a shift from one realm of existence to another. In this context, our universe's fate is just one among many in an endless cosmic sea. The multiverse theory also implies that somewhere, in some universe, every possibility exists. There could be universes where the Big Rip occurs, others where the Big Crunch resets everything, and still others that end in heat death. If the multiverse exists, it would mean that every cosmological fate we've discussed is simultaneously true, with each scenario playing out in different universes. This perspective suggests that the ultimate fate of our universe may not be as significant in the grand scheme, as it becomes just one of countless realities. Yet, it also means that the nature of reality itself might be fundamentally unknowable, as every possibility exists somewhere, making it impossible to define a single outcome or meaning for existence. All of these theories, the Big Rip, Big Crunch, heat death, and the multiverse, present different visions of the universe's end, each fascinating and terrifying in its own way. Yet, as we delve into these cosmic mysteries, we are reminded of the limitations of our own understanding. The universe is not obliged to conform to our expectations, and the true fate of the cosmos may be stranger and more beautiful than anything we can currently conceive. The ultimate ending, if there is one, might elude us forever, just as the stars are unreachable despite shining above us. Our journey to understand the universe's fate is a journey through our own existential questions about purpose, survival, and the boundaries of human knowledge. Even if we never reach the answers, the pursuit itself is meaningful. In exploring the mysteries of the cosmos, we stretch the limits of human imagination and confront the vastness of existence. The mystery of the universe's shape and fate may remain unsolved, but it continues to inspire humanity to look outward, to wonder, and to seek understanding in a universe that is endlessly mysterious, yet endlessly compelling. In contemplating the various theories on the universe's end, we're compelled to reflect on humanity's place within these vast cycles. If the universe truly has an ultimate fate, whether it's a cataclysmic collapse or a slow fading into darkness, then the existence of sentient beings, capable of asking these questions, becomes all the more remarkable. The universe, through billions of years of evolution and cosmic events, has produced a form of life capable of introspection, curiosity, and even awe. This fact alone suggests that conscious thought might not be an insignificant byproduct but rather a unique phenomenon that embodies the universe's own self-awareness. The Big Rip, Big Crunch, heat death, and multiverse hypotheses are not just scientific speculations but philosophical provocations. They invite us to imagine realities and endings that far exceed the human scale, urging us to think beyond our immediate existence. In considering these theories, we are also forced to face questions of value and meaning. Does life have intrinsic worth if the universe is doomed? Are our experiences merely fleeting sparks in the darkness, or do they contribute to a larger narrative that stretches beyond one cosmic cycle or universe? These questions do not have easy answers, but they underscore a profound truth about human nature. Our search for meaning is relentless, even in the face of an indifferent cosmos. The concept of the Big Crunch, for example, carries with it a strange kind of hopefulness. In this scenario, everything that exists today could one day collapse back to a single point, only to be reborn in a new Big Bang. Some theorists even speculate that each cycle might retain faint echoes of previous universes, perhaps manifesting as slight variations in physical laws or initial conditions. If consciousness or memory could somehow bridge these cycles, then each universe would be part of a greater continuum of existence. Even though each cycle would be separated by an era of unimaginable density and heat, the fundamental structure of the cosmos might carry some essence of what came before. This line of thinking connects to the idea of a cosmic memory, or eternal recurrence, a concept that philosophers like Friedrich Nietzsche explored, albeit in a different context. In Nietzsche's vision of the eternal return, every event in life would repeat indefinitely, meaning every joy and sorrow would recur throughout eternity. Applied to cosmology, this implies that perhaps every universe is predestined to replay its entire history, from the formation of galaxies to the emergence of life, over and over in an endless loop. If true, this would mean that humanity itself is woven into the fabric of existence, destined to reappear in every iteration of the cosmos. The Big Rip, by contrast, presents a more unsettling scenario. Instead of a rebirth or cycle, the Big Rip envisions a universe accelerating towards disintegration, leaving nothing intact. This raises questions about the very nature of existence. If everything is ultimately torn apart, then does anything we create, whether cultures, memories, or knowledge, truly matter? Some might argue that the beauty of life is enhanced by its transience, that our actions gain value precisely because they are temporary. Yet, the Big Rip challenges this notion by suggesting a universe where even the underlying structure of reality disintegrates, making any lasting significance impossible. The philosophical implications of the Big Rip are particularly poignant when considering our connection to the stars and galaxies. Every human civilization has gazed at the stars, drawing inspiration and wonder from their permanence and beauty. The Big Rip takes that stability away, revealing a universe in which even the stars and galaxies are not immune to the ravages of time. In this vision, the cosmos becomes a place of inevitable decay, where even the forces that bind particles are overpowered by the relentless pull of expansion. It's a universe without sanctuary, where everything, from atoms to galaxies, is pulled apart and scattered into oblivion. In contrast, the heat-death scenario offers a more tranquil but equally desolate end. Here, the universe doesn't break apart violently but rather fades into a state of perfect equilibrium. In the final moments of heat-death, entropy reaches its maximum level, meaning that energy can no longer flow, and all processes come to a standstill. This outcome raises profound questions about the nature of time itself. Time, as we understand it, is marked by change and the passage from one state to another. In a universe frozen in stasis, time would lose its meaning, stretching forward endlessly with nothing to mark its passage. Some theorists suggest that this timeless, unchanging state might even represent the true nature of reality, a kind of cosmic void where existence becomes indistinguishable from non-existence. This is reminiscent of ideas found in Eastern philosophies, such as the concept of nirvana in Buddhism, where the self and all distinctions dissolve into an eternal, unchanging state. Whether or not this comparison is accurate, the heat-death scenario certainly evokes similar notions of ultimate stillness, where individuality, movement, and identity disappear in a universe where all distinctions have faded. In the face of these unsettling prospects, the multiverse theory offers an intriguing alternative, suggesting that even if our universe ends, countless others may persist or be born anew. This raises the possibility that life and consciousness could emerge in multiple universes, each with its own unique physical laws and evolutionary pathways. If true, then the universe we observe is just one chapter in an endless multiverse library, filled with realities we cannot yet comprehend. The multiverse theory challenges the concept of a singular end to existence, suggesting instead an infinite variety of beginnings and endings across different dimensions. Some versions of the multiverse hypothesis even propose that universes can interact or influence one another in subtle ways. If this were possible, then the death of one universe might serve as the birth of another, or perhaps even lead to a spawning of new universes. This notion aligns with some interpretations of quantum mechanics, where particles exist in multiple states simultaneously until observed, leading to a branching of realities. In a multiverse framework, each of these branches could represent an entirely new universe, each with its own distinct timeline, physical constants, and cosmic destiny. The multiverse also poses an intriguing possibility for the survival of consciousness. If consciousness is not merely a byproduct of matter but a fundamental aspect of reality, then it might find ways to persist across different universes, even if individual selves do not. In a multiverse, consciousness could theoretically migrate or reappear in new forms, transcending the limitations of any single universe's lifespan. While this idea is highly speculative, it underscores the mysterious and profound nature of both consciousness and the cosmos. The exploration of these cosmic fates, the Big Rip, Big Crunch, heat-death, and the multiverse, highlights the vast range of possibilities that lie ahead, each with its own unique implications for existence, meaning, and purpose. As we gaze deeper into the cosmos and unravel its mysteries, we confront the limits of human knowledge and the enigmatic nature of reality itself. Every new discovery brings us closer to understanding the ultimate fate of the universe, yet each answer seems to reveal even deeper questions, suggesting that the mystery may never be fully solved. Whether the universe ends in silence, chaos, rebirth, or transcendence, our journey to understand it reveals something essential about the human spirit. We are driven by a relentless curiosity, a desire to know the unknowable and to find our place in the cosmos, even if that place is fleeting. In pondering the shape and fate of the universe, we also ponder ourselves, our origins, our significance, and our destiny. We may be small in the face of the vast cosmos, but our search for understanding makes us part of something much larger, a cosmic story that transcends any single life, generation, or civilization. As we continue down the path of cosmological inquiry, the mysteries surrounding the universe's fate serve not only as scientific puzzles but as profound reflections on the human experience. Every theory, the Big Crunch, Big Rip, heat-death, and multiverse hypothesis, asks us to imagine a future far beyond our lives, beyond the history of our planet, and even beyond the age of the stars themselves. These theories form a bridge between scientific exploration and existential contemplation, allowing us to consider the true breadth of our existence within the cosmic landscape. The Big Crunch, for example, envisions a universe that undergoes a grand contraction, collapsing back into a state of near-infinite density. This theory suggests a cyclical model, where each crunch leads to a new bang, implying a potentially endless series of universes, each arising from the ashes of the one before. While science has yet to find conclusive evidence of such cycles, the idea resonates with the concept of eternal recurrence, a notion found in philosophies. It's a concept that invites us to consider whether everything that exists is destined to be reborn in some form, giving our lives a unique yet repetitive role in the ongoing story of the universe. In a hypothetical Big Crunch scenario, the universe's eventual collapse would be a gradual process. As expansion slows, gravitational forces would start to dominate, drawing galaxies closer together. The dark energy that currently accelerates cosmic expansion would weaken, and the universe would enter a phase of reverse expansion. Over billions of years, stars and galaxies would crowd ever closer, merging and interacting in increasingly intense gravitational dances. The once orderly cosmic web would become a chaotic cluster of galaxies, ultimately merging into a supermassive structure, a cosmic inferno where heat and density rise to unimaginable levels. If this collapse continues, all matter would be compressed, and the universe would shrink in size until it becomes a singularity, a single point where the laws of physics as we know them break down. Such a state mirrors the conditions theorized at the start of the Big Bang, leading some cosmologists to speculate that the end of one universe might trigger the birth of another. In this vision, the Big Crunch does not signal a final end but rather a transformative phase in an infinite cosmic cycle, with each iteration potentially different from the last. The idea of a cyclical universe has captivated humanity for centuries. This cyclical view of time stands in stark contrast to the linear perspective that dominates much of modern thought, suggesting instead that everything that exists, including life and consciousness, may be part of a cosmic rhythm that stretches across epochs. On the other hand, the Big Rip offers a more unsettling view of the universe's future. Unlike the Big Crunch, which proposes a finite and transformative end, the Big Rip envisions a reality where the very fabric of the cosmos is torn apart by the accelerating expansion caused by dark energy. In this scenario, galaxies, stars, and even atoms would eventually be pulled apart by the relentless expansion, leaving nothing but isolated particles drifting in an empty void. If the Big Rip hypothesis is correct, it could mean that the forces we understand as binding the universe, gravity, electromagnetism, the nuclear forces, are not as permanent as they seem. Over time, dark energy would gain strength, gradually overpowering all other forces. At first, galaxies would drift apart, then stars within galaxies, and finally the very atoms themselves. This would lead to an ultimate disintegration of matter, a cosmic dissolution where nothing remains connected, and space itself stretches into infinity. The Big Rip challenges the human desire for order and permanence, suggesting a universe that is fundamentally unstable and governed by forces beyond our control. It presents a stark reminder of our vulnerability, both as individuals and as a species. The Big Rip's vision of a fragmented universe, devoid of structure, compels us to confront the transitory nature of all things. Everything we know and cherish, our planet, our culture, our sense of self, would ultimately be swept away in the relentless flow of cosmic expansion. Then, there is the heat-death theory, perhaps the most haunting of all. Unlike the explosive energy of the Big Crunch or the violent disintegration of the Big Rip, heat-death implies a quiet, gradual decline into a state of eternal stasis. In this model, the universe continues to expand, but with each passing moment, energy becomes more evenly distributed across space. Stars eventually burn out, galaxies drift apart, and all matter decays into fundamental particles. Over an inconceivably long span of time, the universe approaches a state of maximum entropy, where no work can be done, no new structures can form, and all motion ceases. Heat-death represents a universe in its final stage, an empty, motionless expanse where nothing changes. Without any temperature differences, there can be no thermodynamic processes, no flow of energy, and no potential for life or growth. In this silent, timeless void, existence becomes indistinguishable from non-existence. The heat-death theory is unsettling in its absolute finality, depicting a universe that does not end in a spectacular cataclysm but fades slowly and quietly, like the last note of a symphony that reverberates into silence. The idea of heat-death touches on deep philosophical questions about purpose, existence, and the nature of time. If time is essentially change, then in a timeless, unchanging universe, time itself would cease to exist. The heat-death scenario suggests a reality in which even the concept of end loses its meaning, as there would be nothing left to mark the passage of events. This eternal stillness, devoid of any narrative or structure, forces us to reckon with the idea of a universe where all distinctions disappear, and with them, any trace of the human experience. In contrast, the multiverse theory offers a radical departure from these singular fates, proposing instead an infinite number of universes, each with its own unique laws, structures, and destinies. According to the multiverse hypothesis, our universe is just one of countless others, existing within a larger cosmic framework that may include dimensions beyond our comprehension. If true, then the fate of our universe might not be the fate of all existence, but merely one thread within a vast cosmic tapestry. The multiverse hypothesis presents a tantalizing idea that our universe's eventual end, whatever form it takes, could be insignificant in the grander scheme of things. If there are indeed multiple universes, then each one may undergo its own unique birth, evolution, and death, with no overarching fate for the multiverse as a whole. This view allows for a diverse array of cosmic realities, where every possible outcome, every combination of physical laws, could be explored across different universes. Some versions of the multiverse theory suggest that these universes are connected in ways we cannot yet understand. For example, in the bubble universe model, each universe is a separate bubble in an infinite foam of universes, constantly forming and expanding. Others speculate that quantum events cause universes to branch, creating a new reality for every possible outcome of every event. This branching model aligns with the many worlds interpretation of quantum mechanics, where each possible state of a particle leads to a new universe, effectively creating an infinite number of parallel realities. If consciousness is a fundamental property of the multiverse, it might mean that each universe contains some form of self-awareness or sentient life, potentially enabling life to continue in various forms across different dimensions. This idea offers a faint hope that even if our universe fades or collapses, life and consciousness could persist elsewhere, evolving in forms and ways that we cannot currently imagine. In this sense, the multiverse theory offers an optimistic alternative, suggesting that existence, in some form, may be eternal. The multiverse concept also resonates with the age-old question of why the universe exists at all. In a single universe, one might search for a singular reason or cause for existence. However, in a multiverse, existence itself may not require explanation. It could be seen as an inevitable outcome of infinite possibilities. The multiverse theory thus shifts the focus from "why is there something rather than nothing?" to "how many kinds of something can there be?" As we delve into these diverse theories, we are not only expanding our understanding of cosmology but also enriching our perception of existence. Each model, whether it's the Big Crunch, Big Rip, Heat Death, or the multiverse, contributes to our grasp of reality's boundless possibilities. They reflect our drive to comprehend the vast unknown, even when the answers we find lead to more questions. Our curiosity about the universe's fate reveals something profound about human nature, an insatiable drive to understand the origins and eventual destiny of all that exists. We are cosmic explorers, navigating a mystery that spans eons and transcends the limits of our current knowledge. These theories may one day be proven or disproven, but our journey to explore and understand them speaks to the essence of what it means to be human. Whether the universe ends in fire, silence, endless cycles, or through the unfolding of countless parallel worlds, our pursuit of these answers enriches the universe itself. For as long as there are beings willing to ask, why? The cosmos remains a place of wonder, filled with the potential for discovery and the promise of revelation. The exploration of the universe's shape and fate has profound implications not just for science, but also for philosophy, theology, and the very fabric of human culture. Each of the theories we've discussed, Big Crunch, Big Rip, Heat Death, and the multiverse, carries with it a distinct narrative about our place in the cosmos. These narratives shape our understanding of existence and influence how we interact with the world around us. The Big Crunch suggests a cyclical view of time, where every ending is a precursor to a new beginning. It invokes a sense of hope and continuity in a seemingly chaotic cosmos, reminding us that endings may lead to fresh beginnings. Conversely, the Big Rip paints a picture of an unstoppable force, an existential threat that challenges our understanding of stability and permanence. The implications of such a fate provoke a sense of urgency and existential dread, forcing us to confront the fragility of our existence. In literature and art, this theme resonates with dystopian narratives that explore the consequences of unrestrained growth and consumption, mirroring humanity's ongoing struggle with sustainability and environmental stewardship. The Big Rip serves as a metaphor for unchecked ambition and the potential consequences of our actions, pushing us to consider the limits of our expansion, both in a cosmic sense and within our own lives. In stark contrast, the heat-death theory embodies a sense of resignation. The slow drift towards entropy reflects a universe in which all vibrancy fades into a monotonous stillness. This scenario raises profound philosophical questions about purpose and meaning. If the universe ultimately succumbs to a state of chaos and inactivity, what significance does life hold? Many existential philosophers grapple with these ideas, suggesting that meaning is not inherent but rather constructed by individuals. In this light, the inevitable march towards heat-death could serve as an impetus for humanity to find meaning in the present moment, to create joy and connection amid the knowledge of our finite existence. The multiverse theory offers a different angle, suggesting that each decision, each moment, spawns new realities where different paths are taken. This idea can inspire a sense of freedom and possibility, inviting us to contemplate the many potential outcomes of our lives. If every choice leads to the creation of a new universe, then every action holds weight, emphasizing the significance of our decisions in shaping not just our reality, but the infinite tapestry of existence. It speaks to the hope that in some universe, the best versions of ourselves thrive, compelling us to strive for that reality in the one we inhabit. Beyond these philosophical implications, the scientific community is engaged in ongoing research to determine which, if any, of these cosmological models might accurately describe our universe. Observations of cosmic microwave background radiation, galaxy distributions, and the expansion rate of the universe have provided clues, yet the quest for a definitive answer remains elusive. The role of dark energy, which is still not fully understood, is central to these investigations. Some physicists propose that as our tools and methods for observation advance, we may uncover deeper truths that could confirm or refute existing theories. The discovery of gravitational waves, for instance, has opened a new avenue for understanding cosmic events that were previously inaccessible to traditional observational methods. These ripples in space-time provide insight into the behavior of black holes, neutron stars, and other phenomena that could influence our understanding of the universe's fate. Such advancements underscore the importance of interdisciplinary collaboration, combining the expertise of physicists, astronomers, mathematicians, and even philosophers to create a holistic understanding of our cosmic existence. Moreover, the search for exoplanets and the quest for extraterrestrial life challenge us to reconsider the significance of our place in the universe. As we explore distant worlds, the question arises, are we alone in this vast expanse? The potential discovery of life beyond Earth would not only redefine our understanding of biology and evolution but could also provide insights into the nature of consciousness itself. If intelligent life exists elsewhere, what would their understanding of the universe's shape and fate be? How might their existence impact our own narrative? As we ponder these questions, we are compelled to reflect on our responsibility to our planet and to one another. The fate of the universe, whether it ends in a grand collapse, a quiet stillness, or the branching of infinite realities, can serve as a poignant reminder of the impermanence of our own lives and the urgency of our actions. It urges us to cultivate compassion, creativity, and collaboration as we navigate the challenges of our time, seeking not only to understand the cosmos but also to nurture the fragile world we call home. The interplay between our understanding of the universe and our moral imperatives can inspire a profound sense of stewardship. As we gaze at the stars and contemplate the vastness of space, we are reminded of our shared humanity and the interconnectedness of all life. The scientific pursuit of knowledge, when coupled with a commitment to ethical responsibility, can guide us toward a future where we respect the delicate balance of existence, both on Earth and beyond. As humanity progresses into an era of advanced technology and space exploration, we stand on the precipice of a new chapter in our cosmic story. Theories of the universe's shape and fate have implications that extend beyond theoretical physics. They shape our cultural narratives, influence our philosophical inquiries, and guide our ethical considerations. The questions we ask today will determine the legacy we leave for future generations, echoing through the cosmos as they too seek to understand their place in the grand tapestry of existence. Whether the universe ultimately contracts, rips apart, fades into darkness, or unfolds into an infinite multitude, our journey of inquiry remains vital. In our quest for knowledge, we engage in an act of creation, crafting meaning, building connections, and nurturing hope in a cosmos filled with uncertainty. The mysteries of space are not merely puzzles to be solved, they are reflections of our deepest aspirations and fears, inviting us to explore the unknown with curiosity and courage. The theories surrounding the shape and fate of the universe illustrate the richness of human thought and the complexity of existence itself. From the potential cyclical nature of the Big Crunch to the unsettling implications of the Big Rip, the quiet resignation of heat-death, and the infinite possibilities of the multiverse, each scenario presents unique insights into our reality. As we explore these mysteries, we not only deepen our scientific understanding but also engage in a profound exploration of our humanity, our hopes, our dreams, and our shared destiny in the cosmos. Ultimately, the cosmos may be indifferent to our existence, but our pursuit of knowledge and understanding is a testament to the resilience of the human spirit. Each question we pose about the universe, every theory we develop, and every discovery we make contributes to a narrative that binds us together as explorers of the unknown. As we continue to gaze into the depths of space and contemplate the mysteries of our existence, we may find not only answers but also the enduring wonder that fuels our journey through the stars. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.